So, folks, we were talking about, we started talking about systems with 2 degrees of freedom, right? Just a little bit of review. These are the slides from previous class, and I think this is the one, even this is the one is from class before previous class. Talked about what is the concept of degree of freedom, right? We start looking into system with 2 degrees of freedom with all the components possible, spring, dampers, forces, and we derive the equation of motion for both degree of freedom. We said we have the same number of equations as the number of degrees of freedom in a system. So in this case, we have a system with 2 degrees of freedom. We are going to have two equations of motion. We saw how we can actually write it in a matrix form, and we said if we write it in a matrix form, we're going to end up having a mass matrix, stiffness matrix, damping matrix. Very similar to what we had in a typical system, a spring mass damper on under force vibration. Here we have a spring mass damper, the similar form of the equation, but in a matrix form, and we have also the force. Now we said let's just focus on a simpler system first, and we can define a couple of concepts and important I would say again concepts related to systems with 2 degrees of freedom. These are not new concepts, but these are we're going to expand what we learned for a system with 1 degree of freedom, which basically were systems that we have been covering so far this semester. So let's focus on a conservative system, a system with no damping, so the energy is not dissipated with any specific element. So obviously it's an idealized situation. So in that case, dampers, we put the damping coefficient 0, we put forces 0 because we want to also focus on a system that is not under force vibration. That would be our next step. But first, let's just focus on a system with 2 degrees of freedom under some initial condition or free vibration of 2 degree of freedom system, and that system has no damping. So we said, well, we went through the math, we assumed some solution in the form of harmonic function, and then we said, well, if we do the math and we put things together, we assume the system is moving in a harmonic motion or the motion is harmonic, we'll end up having an eigenvalue problem. Right? And we said, well, solving that eigenvalue problem, we're gonna get two values, right? Two roots. We get the characteristic equation, and characteristic equation gives us two roots. Those roots are, we define them as we talked about this before. These are eigenvalues, the square root of these eigenvalues in the context of vibrations, mechanical vibrations. They are going to be natural frequencies. I said, well, that's how we define natural frequency. And I said, for number of degrees of freedom we have, if we have 2 degrees of freedom, we're going to get two natural frequencies. If we have 1,000 degree of freedom, we're going to get 1,000 natural frequencies. Right? The number of natural frequencies we get is equal to the number of degree of freedom of the system. Then I introduced the concept of mode shapes. I said this is a little different, right? This is not what we had before. Natural frequency we had before, at least we had one natural frequency. Now in terms of a 2 degree of freedom system, we have two natural frequencies. I defined the concept of mode shape, and I said, well, mode shape is the shape of the system, or in a better sense, it's the ratio of amplitudes when the system is oscillating in its first natural frequency. Remember, system has two natural frequencies, omega 1 and omega 2. Now, system can oscillate in its first natural frequency, system can oscillate in its second natural frequency, system can oscillate in some random frequency that is neither first natural frequency nor second natural frequency, right? Think about resonance, the concept of resonance for systems with 1 degree of freedom, systems with 1 degree of freedom. Frequency of excitation or could be anything, right, if we had the force applied to the system. But it could also be equal to natural frequency, which we had resonance. Now here also the system can oscillate in either first natural frequency or second natural frequency, or in a frequency that is neither of them and it's a combination of both. We'll see how to deal with that. But if system oscillates in its first natural frequency, the ratio of amplitudes, right, x1 and x2, or if you remember the solutions we proposed, harmonic solutions, we said x, I'm going to go back a little bit. We said x, the solution we proposed was x1 sine omega t minus phi and x2 sine omega t minus phi. Now, if that omega is omega 1, then x1 and x2, well, they represent where each mass is at any given moment if the system is oscillate in omega 1. So if the system oscillates in its first natural frequency, the ratio between amplitudes are represented by this. x1 is vector. x11 and x12 are two constants. They show the amplitude. If the system oscillates in its second natural frequency, it's oscillating with omega 2, then we can represent the ratio of amplitudes, or where these two masses are at any given moment. Think about it this way, using the second mode shape. Now, what are these mode shapes and how do we find them? Well, these mode shapes are actually eigenvectors. Right? Remember, we talked about eigenvalues and eigenvectors. Eigenvalues, the square root of them would be natural frequencies. Eigenvectors give us mode shapes. Why are they important? Because we use them to find the response of the system to any given input. They represent the response of the system to any given input using these mode shapes. We'll talk about it more when we talk about system response. Now, we said, well, let's, for a specific system, be more specific and take a look at what happens there and what is this concept of mode shape. Right? Eigenvalue, and as a result, natural frequency, you have seen it, it's more familiar. Mode shape is something new. We have to actually focus on it a little more and make sure that we get it. Right? Now, I said, well, for the sake of simplification, or for the sake of, I would say, making your life a lot easier and see what happens and what to explain mode shapes, let's just say we have a system that both masses are equal, m1 is equal to m2 equals to m, just m, and the stiffness constants for springs are equal. K1 and K2 are the same. I took it as K. Now, if I plug this in my characteristic equation that I found for the general form system, right? This equation right here, right? If I plug that in, m1 equal to m2 equals to m, k1 equals to k2, it actually has to be k3 as well. So all of them are just k. K3 equals to k. We get this characteristic equation. Find the roots. Roots of characteristic equation are eigenvalues. Square root of eigenvalues give us natural frequencies. First natural frequency in this case is the square root of k over m. Second natural frequency is square root of 3k over m. Remember, these are not always the same. It depends on the system, how the matrices are formed, and what are the values. So don't take this as a fixed value. You have to go through the whole process, find eigenvalues and then find the roots to find natural frequency. In this case, we have first natural frequency omega 1, second natural frequency omega 2. Now let's find, that's where we were. Now let's find eigenvectors for each, which are going to be mode shape. Mode shapes of a system. So I said for omega 1, let's say also omega is equal to omega 1. Right? When lambda is lambda 1, omega is omega 1. So how do I find it? Vectors or mode shapes? Well, I go back to my eigenvalue problem here. Right? This one. Now I know what lambda is, or as a result what omega is. I can plug that in and find the corresponding x vector, which is going to be the eigenvector for that specific eigenvalue. Right? So let's do it. For this one, but we'll get, let me just write the whole thing. K minus omega squared m, omega 1 is multiplied by x1 will be equal to 0. Well, I'm writing it in matrix form, so write everything in matrix form. So if I expand this, this would be K, and the K matrix would be K1 plus K2 is 2K, 2K minus omega 1 squared. That becomes 2K minus omega 1 squared M, M1 and M2 are the same. Off diagonal element is minus K2, which becomes minus K. Right, this is minus K. And the other diagonal element, K2 and K3 are the same. So 2K minus omega 1 squared M. Same thing. 2K minus omega 1 squared M. I mash them together. K minus omega 1 squared M. And then here we have x1, 1, x1, 2. Two components of this vector. 0, 0. All right, so let's do the math there. All right, the first one gives us 2. Let me see if I have the expanded version here. Might make our life a little easier. All right, we have to actually plug it in. That's easier right there. Omega 1 is square root of K over M, so omega 1 squared would be K over M. And this would be K over M. If you do the multiplication, K over M times M becomes K. 2K minus K is K. So that gives you K. Let me see. K. Yes. So it gives you K x1, 1 minus K x1, 2 is equal to 0. First row times multiplied by first column is equal to the first element on the right side. The second row minus K x1, 1, and that'll give you, this one gives you K over M, M 2K minus K is K, so that becomes plus K x1, wrong, 2 is equal to 0. Now we said, well, when we want to find the eigenvalues, we always get these two equations, two unknowns. The problem is both of them are same equation, so we have to take one variable as free variable. And in this case, I take, let's take, and we said as much as possible, try to go with something simple and take one of them as 1 and see what the other one becomes. So take x1, 1 as 1. It's free variable. If I do that, the first one, well, x1 is equal to x2, right? So if x1, 1 is equal to 1, you can use either of these equations to find x1, 2, which is 1. So your first, not the color I wanted, your first mode shape becomes 1 and 1. This is your first mode shape. Let's see, what does this mean? Here is our system with no spring and damper, no damper, sorry. So let's say this is our system and no external force, and M1 and M2 are equal. So this is where the equilibrium point is at the beginning. Now, if this system oscillates at its first natural frequency, when omega is equal to omega 1, right? The response of the system, we know the form of it is in the harmonic form. If omega is equal to omega 1, in that sign omega t minus phi, what does this mode shape tell us? It tells us that, let me draw it here. It says x1, 1, x1 is 1 and 1, meaning x1, 1 is 1, x1, 2 is 1. As I said, this is a ratio between amplitudes. It means when mass 1 moves 1 unit, mass 2 moves also 1 unit. Well, that's a ratio. So what does that mean? It means if mass 1 moves 0.5 unit, mass 2 also moves 0.5 unit, 5 unit in the same direction. They're both positive. If mass 1 moves, moves minus 1 unit, 1 unit to the negative, mass 2 also has to move 1 unit towards negative. In its simplest form, think about it this way. If it's oscillating in omega 1 and m1 is 1, it goes 1 unit to the right. Mass 2 also has to go 1 unit to the right. So at any given moment, think about these two masses. They oscillate together. At any given moment, if mass 1 goes 0.1 to the right, mass 2 goes 0.1. 0.2, mass 2 goes 0.2. They move together in this case. If mass 1 goes to the equilibrium point and going to a negative, if it goes minus 0.1 to the left, mass 2 also goes minus 0.1. They go to the left together. Because the ratio should always be 1 to 1. Ratio between amplitude. So if one of them is going minus 5, the other one has to go minus 5. So the ratio is always 1. That's the concept of mode shape. It gives us a sense of how the amplitude changes at a specific frequency, at a specific natural frequency, the corresponding natural frequency. Let's take a look at the second mode. Right? For lambda equal to lambda 2, meaning that omega is omega 2. If I draw that, if I do the math or calculation, you will get 2k minus omega 2 squared m minus k 2k minus omega 2 squared m. Now in this case, well, let me be consistent. Maybe I should use vector form. x2, 1 and x2, 2. This is the second mode shape. Second eigenvector. I represent that with x2. Now x2, this whole thing is x2. Has two elements, x2, 1, x2, 2. Now, replace the value. Omega 2 is 3k over m. All right, 3k over, let me clean this. Going back. There it is. This is omega 2. Omega 2 is the square root of 3k over m, and then omega 2 squared because 3k becomes 3k over m. If I do the math, m and m, so this becomes minus k, minus k, minus k, minus k, x2, 1 and x2, 2 is equal to 0, 0. If I rewrite that, that'll become minus k, x2, 1 minus k, x2, 2 is equal to 0, and minus k, x2, 1 minus k, x2, 2 is equal to 0. Remember, we talked about finding eigenvalues and eigenvectors. We went through this. It's the same process. Now, we take 1 as a free variable. Let's take x2, 1, 1. What happens? So x2 becomes, well, if this is 1, this is 1. From either of these equations, the other one becomes minus 1. And this is the second mode shape. Second mode shape. Let's take a look at the system in similar fashion. Let's say this is the system we have, right, in a equilibrium position. Now in this system, let's say when it's oscillating at, for omega is equal to omega 2. The system is oscillating at omega 2, square root of 3k over m radian per second. Now, what does this tell us? Mode shape tells us that the ratio between amplitudes is 1 to minus 1. What does that mean? It means if mass 1 goes to the right, my right, 1 unit, mass 2 goes to the left 1 unit. Mass 1 goes to the left 1 unit, right? Magnitudes are the same. Mass 2 goes to the right 1 unit. So they oscillate like this in their second mode. They always keep this ratio 1 to minus 1. So whatever mass 1 is, if it's 0.1, mass 2 should be minus 0.1. If mass 1 is minus 5, mass 2 should be plus 5. So that would be the system oscillation. If let's say mass 1 goes to right 1 unit, I draw it in a little tight. So this is the equilibrium point. This is just for a given second. 1 unit to right. Then mass 2 has also, I have to, all right. Comes to the left 1 unit. Because the ratio should be 1 to minus 1 for this mode. So that's what mode shapes tell us. They tell us about the ratio of amplitudes, ratio between amplitudes. Now, why are they important? We'll get there. When we start looking at how to find the system response to some given initial velocity or displacement or some external force, that's how we use mode shapes. Mode shapes, you can think of mode shapes as unit vectors in a modal space. So remember, you know the Cartesian coordinate system in space, right? X, Y, Z coordinate system. We represent any vector using 3 unit vector, I, J, K. Or in 2-dimensional, we represent any vector using I and J, unit vectors, right? Now, think about mode shapes as unit vectors in a modal space. What is modal space? Modal space is this. It's not a physical space. You take systems from physical space like X coordinate, Y coordinate, X, Y, Z coordinate, and take it to modal space because it's easier to solve the equations there. It's like a transformation, similar to when we use Laplace transform or Fourier transform, or when we what other transform do you guys know? Maybe these two are the ones you know. Mode shapes help us to represent the system's response, to represent the system response. So think about them as unit vectors again. Think about that. You have some system with 2 degrees of freedom, some force is applied to it, or it's free vibration, some initial velocity or displacements are applied to it. We want to find the response of the system. That's where mode shapes come into play. Because any response, any system response, this is true for linear systems or systems we deal with. Any response of the system is a response of the system to any input, whether it's initial velocity, displacement, some external force, is a combination of mode shapes. Right? Very similar to the way you say any vector in a space is a combination of I, J, and K in 3D space, unit vectors. Right? So any vector can be represented by a combination of I and J in 2D space and I and J and K in 3D space. Now, in modal analysis, call it, any system's response to any given input can be represented using mode shapes. All right, we'll talk about this more and see how this works. But this is the concept, the higher level idea of mode shapes and natural frequencies. Let's take a look at one example, go through the whole example from the beginning to the end, and then I will actually have a couple more sample problems. I can post them. I'll post them 2 more sample problems. You can take a look and see how this process works. And the whole idea of responses being functions or can be represented using mode shapes and natural frequencies is why we need to be very comfortable with finding natural frequencies and mode shapes. So we're going to practice that. All right. We have a system, spring mass system, and that is in the form of, let me draw it here. We have one mass here, another mass there. Let's move it a little further. There's a spring there. Let's make it. This is M1. This is M2. This is K1. K2. I think I took this is K3 and this is K4. Before I get deep into this example, any question about what we talked before? Hope it makes sense that why did we talk about eigenvalues and eigenvectors before we start talking about systems with 2 degrees of freedom? Stop me if you have any question. Type it in the chat box or unmute yourself and just go ahead. All right. All right. So the question is, find the natural frequencies and mode shapes for this system. We're also given some values. We're given M1 is equal to 1 kilograms. M2 is equal to 2 kilograms. And the series of K values. K1 is 1 Newton per meter. K2 is 2. And I think it goes that way. K3 is 3. Also, we get K4 as 1. So the system parameters that you need. All right. So we have to, this is the process. We have to draw the free body diagrams, find the mass and the stiffness matrices. Once we find those matrices, we have to find eigenvalues for that eigenvalue problem that we form using mass and stiffness matrices. And once we find eigenvalues, square root of those would be natural frequencies. From there, we can plug in each eigenvalue to the eigenvalue problem and find the mode shape. Well, that's the, how can we answer this question? Okay, let's get started. Remember, I said, well, the first thing you gotta do is you have to make an assumption about your degrees of freedom. Let's call this x1 and call this x2. Said, well, first of all, they both should go in the same direction in your assumption. Second of all, you have to assume, you have to make an assumption about which one is bigger than the other one. That always should be this thing that you do, otherwise you get confused for drawing free body diagram. So in this case, I'm going to say x1 is greater than x2. I give you the degrees of freedom most of the time, especially if it's a little confusing or complicated. For simple systems, you can always figure out what is x1, x2. All right. So x1 is greater than x2. Let's draw the free body diagram. Free body diagram for M1. This is the part that a lot of mistakes happen. X1, I explained this before. X1 is greater than the X2. So if this M1 is M2, assume that the one with lower amplitude is fixed when you're looking at the one with higher amplitude. So M1 is going this way. Assume that M2 is fixed. It's going this way. So K1 is trying to pull this back to where it was. I'll just draw the freeway diagram right here and use this space in an optimal way. This is M1. Right? K1 is trying to take it this way. K1, X1. Well, I have to put it, it's not exactly right there. Let's be more meticulous. K1, X1. Now, for what is between them, M1 is going towards M2. So the spring between these two is under compression, meaning that the spring wants to push. Remember, a spring and dampers want to make push the system or masses, whatever they're in contact with, towards their initial position or towards their equilibrium position. So K2 is pushing M1 back. So that would be the direction. What would be the magnitude? X1 is greater than X2. What should I put for the magnitude? Now I know the direction. Does anyone remember that? All right.
X2 minus X1.
The other way around. Because we said once we decide about the direction and we know the right direction, which we know now, we always keep the magnitude positive. I'm going to emphasize this. You're going to have a quiz on this, and I'm sure good number of you are going to make this mistake. That's why I keep saying this, that figure out the direction, keep the magnitude positive, always. So since X1 is greater than X2, X1 minus X2 would be the positive. Pay attention to this. You make a mistake here, the rest just goes wrong. You know, the equation motion becomes wrong. Then the matrix form of the equation is wrong. The matrices are not going to be symmetric, which I told you it should be always the case in this course. So be very mindful of that. And this is the direction. So M1, X1, double dot. So write the equation. Summation of forces is M1, X1, double dot. We get minus K1, X1 minus K2, X1 minus X2 is equal to M1, X1, double dot. I'm going to move things around. M1, X1, double dot. This becomes plus K1 plus K2 goes to the other side. X1 minus K2 X2 is equal to 0. That would be the first equation. Hopefully I did not make many mistakes. You'll see. At the end, it's going to be obvious if a mistake is happening. Right. Looking at the second mass. Free body diagram for M. Technically, I'm drawing both free body diagram and kinetic diagram. But I'm I don't know, it's a 10 for it. I can be very technical and say I'm trying to save time by not writing it, but I'm mostly kind of a little lazy. You know what I mean when I draw the right freeway diagram. All right, so M2 is going to the right. First, forget about M1 in this scenario and its connection to M1. Just M2 itself is going to the right. Because it's going to the right, K4 is trying to push it back to where it was. K4, the only displacement for that is X2. There's no connection with anything. The wall is fixed. M2 is going to the right, so K3 is trying to pull it back to where it was. There goes K3. Pay attention. K3 is the connection between M2 and the wall. So the displacement is just pretty much X2. Very important. This is not a connection between two masses, right? So the displacement is just X2. Now let's get into K2 that is between these two masses. Well, what is the direction? Well, if M1, X1 is greater than X2, and we put, you can look at the free body diagram for M1, K2 X1 minus X2 is the magnitude. We know that's the magnitude because that's the magnitude should always be positive. K2 X1 minus X2. The direction, well, if the direction on M1 is this way, the direction on M2 should be other way. All right? Newton's third law. Apply force to each other, one should be the opposite direction, the other one, the same magnitude. If you don't want to do it, look at M2, M1. M1 is getting close to M2, so the K2 is under compression, meaning that K2 is pushing M2 to the right. That's the direction. Magnitude, always keep it positive. Make an assumption X1 is greater than X2, so K2 is multiplied by X1 minus X2. That'll give you M2. Well, this is M2. This is also M2. And this is pretty straightforward. M2 X2 double dot. As I said, assumption. Make assumption. Makes assumption that both motions are in the same direction. That's how we get the right equation. All right. Summation of forces is equal to M2 X2 double dot. As a result, you will get minus. If I get this as positive, I have to mention here, I always take the direction of the motion positive. Another important thing that you know from before, when we were dealing with systems with 1 degree of freedom, always direction of motion is positive. Minus K3 X2 minus K2 X1 minus X2 minus K, this is positive, this direction, K4 X2 is equal to M2 X2 double dot. Let's move things around. M2 X2 double dot. Then I'll get plus K3 plus K4 X2. Wrong. Actually, there's one more component for X2. K3, K4, and K2. X2. And then we have K2, X1, which goes to the other side, becomes negative. Minus K2, X1 is equal to 0. This is my second equation. Now let's just convert that into matrix form. That's what we need to do in order to find eigenvalues and eigenvectors, which are not basically eigenvalues give us natural frequency, and eigenvectors are going to be mode shapes. So rewriting this, we have the mass matrix there, X double dot, X1 double dot, X2 double dot. We have the stiffness matrix there. I'm going to make it a little bigger. X1, X2 is equal to the force vector. There is no external force applied to the system, so 0 and 0. All right. The first line would be the first equation. Well, M1, X1 double dot, and then 0, X2 double dot. Because there is no X2 double dot component in the equation 1. This is coming from equation 1, this line. And the second line is coming from equation 2. X1 is multiplied by K1 plus K2, and X2 is multiplied by minus K2. And the other side is 0. That's all for equation 1. Equation 2, there is no X1 double dot. X2 double dot would be M2. X1 is minus K2, right? K2 times X1 minus K2 X1, and then whatever X2 is applied by, multiplied by, which is K2 plus K3 plus K4. This is the matrix form. Matrix form of equation of motion. All right, how do you check? All of the matrices symmetric? Yes. Mass matrix is symmetric. Off diagonal elements are 0. Stiffness matrix is symmetric. Off diagonal elements are the same. They're both minus K2. It's the best check possible. If you get to this point and your matrices are not symmetric, go back to the equation of motion. Equations of motion. You made the wrong assumption somewhere or made a mistake moving things around. Right? Double check. All right. We have this. We have the values. We can actually start finding. So characteristic equation is K. That K minus, should we write it as lambda? Let's write it as lambda. Lambda m times x is equal to 0. This is the general form of the characteristic equation. So well, this is not the characteristic equation. Scratch that. This is the eigenvalue problem. Eigenvalue problem. Now the characteristic equation, can be found by finding the determinant of K minus lambda m and make it equal to 0. We can do that. We have everything we need. Determinant of this matrix is equal to 0, so that will give you determinant of K matrix is K1 plus K2. K1 is 1, K2 is 2, so it becomes 3 minus lambda m1. Actually, I know what m1 is. M1 is 1, so it becomes 3 minus lambda. Second element, well, m has nothing to do with 0. K becomes K, whatever it is, minus K2, and K2 is 2. So this is minus 2. As a result, this is minus 2. And right here, we have K2 plus K3 plus K4. So 2 plus 3, 5, plus 1, 6. That becomes 6 minus lambda. Minus lambda m2, and m2 is 2 kilograms, so 2 lambda. Raise that. Minus 2 lambda is equal to 0. Determinant of this, determinant of a 2 by 2 matrix, we said if you assume that A, B, C, D elements, AD minus BC. So that'll give you 3 minus lambda, 6 minus 2 lambda, minus 4 is equal to 0. Let me make sure that I didn't make any mistake. No. If you move things around here, you get an equation in the form of a second order equation, which would be 2 lambda squared minus 12 lambda plus 14 is equal to 0. This is your characteristic equation. The roots of these are eigenvalues, and the square root of eigenvalues are natural frequencies. We can calculate that. Just use a calculator. This is a second order equation. It pretty much becomes lambda squared minus 6 lambda plus 7. And then you have to find the roots. So I did it already. Lambda 1 becomes 1.5858, and lambda 2 becomes 4.4142. From there, omega 1 is the square root of this, which is 1.2593 radian per second. First natural frequency, omega 2 becomes 2.1010 radian per second as second natural frequency. This is 1 there. This is 1 here. All right. So here are natural frequencies. Natural frequencies. This is the first part of the problem. We were asked to find natural frequencies. Now we're asked to find also mode shapes. Mode shapes are eigenvectors. So for lambda is equal to lambda 1, which we found it as 1.5858. Right? Just plug that into eigenvalue problem. Right? That would be 3 minus 1.5858. Well, this is minus 2. This is minus 2. And then 6 minus 2 times 1.5858. This multiplied by, we are looking for the first mode, so x11, x12. 0, 0. Just numbers. Do the multiplication there. Let me move this minus to the right so it's not mixed with this there. So it gives you two equations. You're gonna get, well, 3 minus 1 point. I already did the math, so it's gonna be 1.4142 x1 1 minus 2 x1 2 is equal to 0. And the second one would be minus 2 x1 1. 6 minus that value turned out to be 2.8284 x12 is equal to 0. I do what I always do. Take 1 as free variable. Take x11 as 1. As a result, you will get x1 as, well, this is 1. We took it as 1. The other one becomes 0.707. And this is your second mode. First mode. First mode, mode shape. Find the second one, same process. For lambda is equal to lambda 2, right? Which is, how much was lambda 2? 4.4142. 4.4142. Right, I'm just going to write that here. That becomes 3 minus 4.4142 minus 2. Look to the right. Minus 2. 6 minus 2 times 4.4142. And this is going to be x2 because this is x, the second mode. x21, x22. 0, 0. You do the math, you'll get two equations. The first one would be minus 1.4142 x21 minus 2x22 is equal to 0. The second one would be minus 2. Oh, that's obvious. x21. And the second part in this equation would be minus 2.8284 x22 0. Same process. Take, let's say x21 is equal to 1. You can do the other way. You can take it as any number. As I said, I take 1 because it's easy to interpret and look at, but you could take this as 1,000, 1 million, whatever you want to take it. It can be even a negative number. You can take it minus 1 and just find the other one. This is the ratio between amplitudes, and that's why it doesn't matter what you get. It's whatever you get this, as long as the other one follows the same ratio, we're good, because mode shape represents ratios between amplitudes. So if you do that, x2 becomes, well, the first element we put 1. If I did not make any mistake, this becomes minus 0.707. And this is your second mode shape. As easy as that. Now, first mode, if you want to, I guess, imagine or think about what it looks like, this is the first mode. If I draw the general form, M1, and then draw that one there as M2, and then should have been a little longer, so I have the same ground. It looks less weird. There you go. First mode, let's say first mode, if I can squeeze everything here, would be great. First mode, when the system is oscillating with omega is equal to omega 1, which was, how much was that? Omega 1 was, went too far, 1.2593 radian per second, 1.2593. Bad drawing. 1.259. I'm just going to keep it that. Now here is the shape. First mode was 1 and 0.7. Right? 1 and 0.707. Yeah. So that'll give me this. At this frequency, the ratio, if this one moves 1 unit, my masses are becoming smaller and smaller. My desperate effort to make it look like the original one. There you go. This would be M1. If this is the equilibrium, and this is also the equilibrium, and this becomes, I would say, all the way to here, and then draw it right here. M2. If this moves 1 unit, I don't think I follow the correct scale, this should move 0.707. Should always keep that ratio. The second mode, similar to this, but in this case, if this one moves 1 unit, the other one moves minus 0.707. So keep in mind, this ratio should always be the same. If this one moves 0.5, the other one should move 0.707 divided by 2. If minus 1 unit to the left, the other one should move minus 0.707. So at any given moment, remember, it's a function of time. They're oscillating. At any given moment, they should keep that ratio. If the system is oscillating, is first mode. If in the second mode, they keep the ratio as the second mode. All right. Any question about this one, folks? I hope that now the idea of mode shapes and eigenvalues and eigenvectors make a little more sense. We're good? All right. Kindly, I'm explaining things very good way. I would like to interpret it that way, but that's why there is no question. All right. Another example I want to show you. This is something that is actually more practical. Well, not practical, but it's something a little different. For some reason. All right. So let's say we have this is. Let me draw it. Oh, maybe I should use this. Let's say we have a bar like this. Sitting on Why am I using the wrong color? All right, we can just change it just to be consistent. It's sitting on two springs. Now, this is a system with 2 degrees of freedom. Why? This is center of gravity exactly in the middle. Or maybe just make it a little more interesting and put the center of gravity somewhere that is not in the middle. And then this distance from one side to center of gravity is L1. Distance from this side to center of gravity is L2. And then we have, what else? We have properties of this bar, M, and mass moment of inertia around center of gravity, ICG. This is K1 and this is K2. What else? That's pretty much it. Why does this one have 2 degrees of freedom? Well, 1 degree of freedom would be its vertical motion, going up and down, up and down. The second degree of freedom would be because if x1 and x2 do not have same stiffness, if they have different stiffness values. Right? So you have a bar, I do have a bar here as a matter of fact. You have a bar going up and down and rotating. Right? You have something like this, oscillating like this, most probably. So it's not just it goes up and down. This is 1 degree of freedom. The second degree of freedom would be the rotation it has. It oscillates like this. So this is a system with 2 degrees of freedom. So here is what the problem statement says. It's asking us to derive the equation of motion specifically for small angle theta. I'll tell you where theta is. And write them, well, these equations of motion, write them in a matrix form. Theta is, well, let's put it this way. Use theta and x as coordinates, where theta is the rotation about center of gravity. All right, pay attention carefully. That's all we do. I'm going to draw the bar. I'm going to assume that it's coming down, it's rotating clockwise at some given moment, because I want to derive the equation of motions. Equations of motion. That's not what I was trying to do. Let's do it this way. And I don't know why it's so thick. There you go. This is better. And we're going to draw the, I don't even know what that is. So I'm going to draw the second part here, and let's connect them together. X is how much the center of gravity is going down. 1 coordinate. The second coordinate system is, well, parameter for a coordinate system, as the problem says, is theta. The amount this rotates around center of gravity. Here is the center of gravity. We went down x amount, rotated theta amount. Let's draw the Fibonacci diagram. See what can we get out of that. All right. Now, we are going down x amount at the center of gravity. So because we're going down, you see both the springs are compressed. So as a result, we can immediately say, well, the springs are trying to push this system back up. That's not very complicated. How much? The magnitude would be the question. So K1 multiplied by something and K2 multiplied by something. Let's put some dimensions here. This is L1. This is L2. This I'm going to call, let's say, X1. And I'll call this as X2. You remember this, looking at these triangles, when we had this, I'm going to use a different color again so things are more clear. If this is theta, well, this is also theta, right? This is also theta. That's how it's rotated. So this distance right here, the amount, this is the amount that the spring is stretched. This distance here, not the color I wanted. This one. This is how spring 1, K1 is compressed. And this is how much spring 2 is compressed. I don't, well, let's just put X1 and X2. Well, Y1 and Y2. This is where the equilibrium point was at the beginning of the motion. Went down X amount, right? This is X. Maybe I should use the right notation if I take this as X. So let's just do everything in X and Y direction. So let's take this as Y1 and Y2 and X1 and X2. All right, from before, we already know that if you look at this, we can write Y1 as L1 cosine theta and Y2 as L2 cosine theta. We know that from before. Now, looking at how much K1 is compressed, X1. X1 would be, well, this, let me write it and then we'll see. X minus K1 would be X, the center, and this side went up, minus the amount this went up, which would be L1 sine theta. And I'm looking for a small angle, so I'm going to just put it theta. Again, we went down X amount, so X, K1 times X. I'm looking at the force on the left from this one. But the ball is rotated a little bit, so this side went up. How much did it go up? L1 sine theta. Remember, this is the distance I'm talking about. This is L1 sine theta. This is L1 sine theta. So the final position, which is somewhere there, right, would be X minus this amount, L1 sine theta. And theta is small, so I can take sine theta as theta. Same story, a little different from the other side. I have this as X. Now plus this extra amount that this went down because of rotation. And that would be L2 sine theta. Small angle sine theta, I make it equal to theta. So this becomes X plus L2 theta. And that's pretty much all the forces. We start from equilibrium, so we're ignoring the effect of the mass, of weight. On the other side, kinetic diagram, if we draw it here. We have rotation. So this is center of gravity. We have rotation. There you go. We have I CG theta double dot. And also this is going down. So M X double dot. Two components. Linear, and one because of the linear motion, one because of rotational motion. Now let's write the equation. Summation of forces in y direction would be M. Well, we took this as x, so let me put the coordinate there. We took that as x. This is the coordinate in x, and this the coordinate in y. I want to be consistent there. So summation of forces in x direction becomes mx double dot. Right. What are the forces on free body diagram? Well, we have this one is upward, minus k1 x minus L1 theta. And the other one is minus k2 x plus L2 theta. Let's not make a mess there. So I'm going to move this a little bit to the right. L1 sine theta. So K2 x plus L2 theta is equal to mx double dot. You can move things around. You're going to get, I'm just going to give you the answer, mx double dot plus K1 plus K2 x minus K1 L1 minus K2 L2 theta is equal to 0. This gives you the first equation. And you can get the second equation. Summation of moment about center of gravity is ICG theta double dot. And we'll take the direction of the motion always as positive. Remember that. In this case, this one was positive. So you do that. K1 x minus this gives you K1 x minus L1 theta. The distance this force has with center of gravity is CG right there. It's Y1. And let's just simplify things. We can write this. Remember, for a small angle, we can L1 cosine theta is L1, and L2 cosine theta is L2. So this Y1 is basically just L1. We have the other force on the other side. This is negative the moment it creates around center of gravity. So that becomes K2 x2 or x plus L2 theta times Y2. And this is equal to ICG theta double dot. You can move things around, write it in a better way, replace Y1 with L1 and Y2 with L2, obviously, based on the geometry. So you will get ICG theta double dot plus K1 L1 squared plus K2 L2 squared theta minus K1 L1 minus K2 L2 x is equal to 0. This would be your second equation. So just I move things around in the previous equation, in my original equation. You now have equation 1, you have equation 2. All you got to do is to write it in a matrix form. Now, remember, here is the interesting thing you observe. The degrees of freedom are not x1 and x2. That's the difference here. Degrees of freedom are x and theta. So when you write the equation of motion in matrix form, right, you have the mass matrix there. And then here you have x double dot theta double dot instead of x1 dot x2 dot. stiffness matrix, you have x and theta, and there is no forces applied. And the first line comes from equation 1. The second line comes from equation 2. So equation 1, I have m, and then k1 plus k2. All right, so this becomes m. There is no theta double dot. X and theta is going to be k1 plus k2 times x. All right, that was equation 1. Equation 2 is minus k1 L1 k2 L2. So this is minus k1 L1 minus k2 L2. That would be the component then. Equation 2, well, nothing for this, and this one is ICG. Right, in a matrix form, this gives minus, which should be minus k1 L1 minus k2 L2. If it was something different, we would have made a mistake, because this matrix should be symmetric. So whatever is the off diagonal there element, it should be the same off diagonal element here. And the other component would be k1 L1 squared plus k2 L2 squared. I don't know if I can fit it there. We'll see. K1 L1 squared plus k2 L2 squared. And this is the matrix form. Form of equations of motion. So a little different. X, theta instead of x1 and x2. So still system with 2 degrees of freedom. Geometry becomes a little tricky to find out the forces and how much the springs are compressed. Once you get the geometry right, this is just pretty much a dynamics problem. Find the summation of force in x direction, mx double dot, a moment about a specific point. Write those, you get 2 equations. Well, there's nothing in this case in horizontal direction, which we call it y. So I didn't write that. And then rewrote the equation in matrix form. And remember, degrees of freedom now are x and theta. I'll show you one example in next class. Why is it interesting? Because then you can actually model a simplified version of a car, and how does that oscillate, and how as a matter of fact, I can just post that problem for you. We'll see if we get it time to do that. Maybe I'll just post it. I'll post the problem along with this one. I showed you how to derive. I'll post the problem, sample problem, how to actually use the results to analyze the car's motion, or at least find these eigenvalues, eigenvectors, natural frequencies, and mode shapes. And I have 3 more sample problems. It's pretty good. So I'll post 4 sample problems for you related to how to find mode shapes and natural frequencies for different systems, so you can actually practice this. All right.